Hello, welcome to this week 4 of lectures on the course on linear systems theory. And if you have come this far, you are actually doing pretty well, I presume, in the course. So we started off in week 1 with just some general examples of building mathematical models of systems. And of course, we did also investigate certain properties of systems and what can we infer from the models and so on. Week 2 and week 3 were just dedicated to just equipping ourselves with tools from linear algebra, right. So, and these tools would be very useful for us through the remaining 8 or 9 weeks of the course. So, today we will start with some basic state space models, and which are essentially in form of differential equations. And what does the solution of those equations mean? Can we use some properties that we learnt earlier? Some things might be obvious to us, something might be a little new, but they can be kind of derived from the background we already have. So that will that concept is called the state transition matrix that we will spend a bit of time on today. We start with a standard form of a linear state space systems. I am not at the moment talking of outputs, just look at the state equation. X dot is Ax plus Bu. Okay, so I can write this more generally as x dot of t is A t x t plus b of t u of t. So, this is like a linear time varying system, whereas this is just a time invariant system. So, we will deal with both of them and start with a little simpler case of time invariant case, and then slowly build up our case to solve or to look at solutions of time varying systems. Okay, now how to write a state space model for a given system? So, we have done a bit of that in our first course on control engineering, and I think much of you who are listening to this course would have had some course in basic control with a little bit of exposure to state space analysis of systems. So, if not, then you can just revisit those lectures over here. So, I would not want to redo that because it is essentially the very similar kind of stuff that we did over there. So, we will assume that we know how to construct state space models x dot equal to Ax plus Bu, where x is a state vector, u is a input, A is a system matrix, and B is the input matrix of appropriate dimensions. So, the question that we will ask here is, well, given an initial condition of the state x t at t equal to 0, let me call that x 0, and some control input u of t, can we find, right. So, what is given is the initial state of the system and a certain control input. Can we find the state, the value of state at any time t greater than 0, could be 10 seconds, 20 seconds, a million seconds, and so on. Okay. So, essentially in terms of mathematics, in mathematical terms, I am looking at, can I solve this for this equation, right. So, this is a differential equation, can I find a solution of it. So, let us begin with a little example to motivate our case, and also further simplify it by letting u to be a constant input. Yes, like if I take a circuit like this, V will just be 1 volt or 2 volts or whatever. Okay. So, in this system, so I will have a R L circuit with a constant voltage input, and so what is given to me are L and R, which are the constant parameters of the system, the input voltage. So, what I would like to see is the evolution of current. So, as soon as the voltage is applied at say t equal to 0. Let me also assume that the initial current through the inductor and therefore also through the resistor is 0. So, the question is, how do I find the value of current at t equal to say 1 second, 20 seconds, and so on, right. And what will one expect it to be a function of? Well, the current will definitely be a function of course the system parameters, it will also be a function or it will also depend on its own initial condition, right, and of course it will depend on what is the input also, right. So, can we find the current as a function of time and its initial condition is our question, and we would have solved this equation several times in maybe first course on networks, we have possibly even a first course on control engineering, more immediately in a more obviously in a first course on differential equations and so on. So, we will just revisit that in a for our own benefit or to make a bit of continuity or self containment in the course. Okay, so where do I start with? I know that I can write down the differential equation which comes from the Kirchhoff's voltage law, and I can just write a differential equation di by dt is R by L I with a negative sign and Vs over L. Okay, so these things we already know. We also know that well, I can solve. I will use the method of Laplace transforms, right, which was one of our earlier tools that we learned in control engineering or even in mathematics of how to use a certain Laplace transform to solve ordinary differential equations. The advantage comes that it converts a differential equation into a linear equation, so convolutions become multiplications. So, it is a little easier for me to handle, right. So, I just use the Laplace methods and then compute the solution to be of this form, like something depending on the initial condition, something depending on the voltage, and of course, the system parameter R and L, and of course, the variable which is the current here, it evolves over time, and the T is captured over here. Okay, so the system will essentially have two components, or the profile of the current which we are interested in observing will have essentially two components, the natural response and the force response. Okay. So, the natural response or this takes care of the system transients and also with the influence of initial condition. If the initial condition is 0 as we assume, so this term will just go away. So, everything will just be based on this. Okay. So, the two components are the natural response, okay, and then the effect of the external input, the voltage in this case, right. And if you look at it, say assume that I of 0 is not 0, say it is equal to 1. And as time progresses, what we see is that the effect of this term, it goes asymptotically goes to 0. As t becomes very large, this natural response, the term it goes closer and closer to 0, right. So, we can say that this effect of the natural response, of course, I am talking of stable systems here. So, that it's so that the effect is a little natural, that the effect decreases as time progresses, right. So, this is also like the system, a part of the system transients. Then you have the influence of the voltage, and this gets dominant as time increases. So, the effect of the natural response decreases and the force response increases, and then it will so what will remain at the steady state is only the terms corresponding to the force response. Okay. So, what is interesting to observe is this term e power minus r over L t appears in both components. Okay. Now, is this general, or is there any interpretation to this this kind of quantity here, right? An exponential term which of course, which has the time component and also to do with the system parameters. So, we will try to interpret this in a little general setting now. Okay. So, let us start building our case with a scalar system, right. X is just in R as opposed to say R1 as opposed to an n dimensional state vector. Therefore, A and B will just be will also be in R, U will be in R, and so on. So, if x of 0 is the initial condition, then the solution can be written in this way. So, this is in some sense also you could go back to this equation that we had here and then just compare what we are trying to do here, right. So, this is also a first order equation with certain initial conditions, and then I can, if I generally have x dot equal to A x plus B u, I can write a solution which looks like this. Okay. Now, can I do something more, right? Can I write this for an n dimensional system? That is what we will be interested in, and of course, any arbitrarily time varying control signal u of t. So, that is what we will spend time doing that. Okay. So, let us first start with the unforced system. This is equally interesting to look at the solutions of the unforced system. So, essentially let us start with a scalar case x dot equal to a times x, and let me assume that, okay, let us just write down few things here. So, I have x dot is a x, right, everything is in R, x is in R, a is also in R. Okay. So, let me assume the solution to be of the form, say it's like a series in time, right. So, this has b0 plus b1 t plus b2 t square and so on, like a power series in time. Okay. Now, well, is this a solution, right? And if okay, assume that this is a solution, and if this is a solution, then it must satisfy let me call this equation 1, right. It must actually satisfy the equation 1, the ordinary differential equation 1. Okay. So, let me do this, let me differentiate. So, I just want to write it in this way, right, x dot equal to a x. So, on the left hand side x dot, so I just differentiate this, I will have b1 plus twice b2 times 3 times t plus 3 b3 times t square. This is equal to a. So, the a times x, this is my x. So, this will be a b0 plus a b1 times t plus a b2 times t square and so on, right, and all the higher powers. Okay. Now, if this is the solution, okay, let us also assume that x at 0 is some x naught. Okay. If this is the solution, what are the unknowns? Unknowns are b naught, b1 and b2 and so on, right, until infinity. What is given to me? Given to me is the initial condition and this number a. Okay. Now, can I write these b's which are unknowns in terms of what do I know? I know a and I know x naught. Okay. So, let us look at the first term, right. So, and I just equate the left and right side, and then the coefficient corresponding to t square should be equal, like similarly the coefficient corresponding to t should be equal and so on. So, first thing would give me that b1 is a times b naught, okay, and the second expression will give me so this and this, so twice b2 is a b1, or b2 is half a b1, and what is b1? b1 from here is a times b0. Similarly, I look for the third one, 3 times b3 is a times b2, and this will give me b3 as 1 over 3, 1 over 2 a cube b naught, and similarly b k would be 1 over k factorial a power k b naught. Okay. So, I have the solution now in the following terms. So, x of t now is, okay, what is b naught? Okay. So, I have everything in terms of b naught plus what is b1? b1 is a b naught plus b2 times t square. What is b2? Half a square b naught t square and so on. Okay. Now, I have everything now the solution written down in terms of a, which is given to me, and b naught. Okay, how do I find this B naught? Well, B naught is simply the initial condition. X at 0 would simply be B naught, and this will be X naught. Okay, that's easy. And therefore, now I can write down x of t as 1 plus a t plus and so on with x naught. Okay. So, that is what is happening here, right. So, the solution can be expanded into a power series of this way in this form, and I know that this actually is e power a t, right. So, okay, this we know. So, I am just constructing the solution in a slightly better or slightly in a more natural way that one would do before we sophisticated into closed form expressions for all these differential equations. Okay, now I am looking now at the solution to a matrix, so to a vector differential equation. So, this is usually called a scalar differential equation. Just use dE where the states is just in R. Okay. Now, I will go to say vector differential equations when I have x dot of t is a x t, where now x is n dimensional vector, a is n cross n matrix, and then you will have certain initial conditions. The initial state vector would be x 0. Okay. So, let me similarly write as I did in the previous case like this. So, let me assume that there is a solution which looks like this. X of t is, now these are all vectors, right. B 0 is a vector plus B 1 t plus B 2 t square and so on. Okay. Now, how do I verify assuming this is a solution, what are the b's is again it will be the same problem for me, right. So, I just write it again. So, what is x dot would be b 1 t plus, sorry, I differentiate this, I just substitute the value of x into this given differential equation. So, the first term will be b 1 plus twice b 2 t and so on. On the right hand side I will have a times b naught plus a b 1 times t and so on. Okay. So, again I can just do the same trick to find the coefficients, and so again b 1 is a b 0, similarly twice b 2 is a b 1 and so on, right. So, this will give me a solution which looks like this, right. So, I have the enclosed identity matrix A t and all these higher powers of time. Okay. So, of course, this is true. You can easily check by differentiating both sides. That is one of the way to check if a certain x of t is the solution to a particular initial condition or not. So, in the similar way, so this is okay. This is a n cross n matrix. Okay. So, similar to what was happening previously here, this is loosely speaking, this is just A substituted by the matrix A, right. So, we can call this as the matrix exponential okay, or also I can write this as e power a t in the similar way as I had e power a t, where a was a scalar, right, and now I have e with a matrix on top, e power a t, and then of course the initial conditions here. Okay. So, that is just rewriting this again, right, starting from a scalar differential equation to a vector differential equation, right. So, that is the first step towards writing solutions of state space equations, assuming that u is 0. We are not at the moment worrying much about what is the nature of input. So, we just look for autonomous systems x dot equal to a x. Okay. So, We'll pause here for a while and then continue this with this lecture.